Now we are discussing the continuous charge distribution. Continuous charge distribution. So far we were dealing with discrete charges where charges are present at certain points. And now we are discussing distribution of charges along a line. So this distribution is along a line. It can be a straight line or a circular ring or any other distribution that can be described by single line. Alright, now consider thin rod. Thin rod is an example of continuous charge distribution along a line. So we say thin rod, or another example is circular ring. Here we define the charge distribution by density. This density is nothing but the number of charges or the charge, the amount of charge per unit length in the case of linear charge. Thin rod and circular ring is an example of linear charge distribution, linearly distributed. So this is an example of a linear charge distribution. So density is charge per unit length. So density, linear charge density, there is a quantity called linear charge density given by lambda is equal to dq by dx, where q is charge, x is the linear distance, or you can write dq, small charge, equal to lambda times dx. Now this is something like this. You have a thin rod, very thin rod, which says you can accumulate only very finite number of charges along this line. So this is the small distance dx, and the amount of charge dq in the small distance dx is equal to lambda, which is the charge density, linear charge density, times dx, that is equal to dq. So throughout this the distance, that is, if you consider from this length as L, throughout the length of the rod, the lambda is constant. You can also have lambda varying, that comes under the varying charge density. Okay, so in that case we cannot write if lambda is varying. If lambda varies, then we cannot write lambda as dq by dx. It increases, so in some form it may vary. All right, yeah, okay. So uniform charge distribution. This is for uniform charge distribution. Uniform charge distribution means lambda is a constant. uniform charge distribution simply implies that the lambda is constant. So if lambda is constant, the total charge q can be written as integral lambda dx, and this integral will go from 0 to PL, length of the rod, and that since lambda is constant, you can write integral 0 to L dx, that's equal to lambda L. So total charge q is equal to lambda n. Now for a non-uniform, the non-uniform implies lambda is not constant, which means the total charge q is equal to integral lambda dx. You cannot bring this lambda outside because lambda will be a function of x. Depending on x, it varies, so it cannot be brought out, taken out. So the total charge q will remain integral lambda times dx. Considering the length element in different coordinate systems, so length elements, this represent dx, dy and dz in this is in Cartesian coordinate system. Okay, now for considering the polar coordinate system, polar coordinates. So for polar coordinates, the length elements are dr and r d theta. So this is the polar coordinates length element. Now for the cylindrical coordinate system, we have r, phi and z. So let us write down the length element in cylindrical coordinate system. These are dr, rd theta, rd phi and dz. Now for spherical polar coordinates, the coordinates are r, theta and phi, and the corresponding length element are dr, r d theta and r sin theta d phi. So you can also remember the metric element for the Cartesian coordinate system. This is 1, 1 and 1. You can go through the mathematical methods of physics, MMP, vector analysis, vectors, this chapter of our video lecture to understand more about the length element and how to calculate the length element, area and volume in different coordinate systems. So this is the metric element for Cartesian coordinate system, and for polar coordinates it is 1 and r, and for cylindrical it's 1 r 1, and for spherical polar coordinate it is 1 r sin theta. Okay, so this is it. Coming to the two-dimensional continuous distribution of charges, two-dimensional continuous. charges. Now here the examples are disk, so instead of the linear charge density, here we have surface charge density. And sigma is equal to, the surface charge density is given by sigma, that is equal to dq by dA. The A is the area, so the total charge or the small charge dq is given by sigma times dA. Now for a uniform charge distribution, you have sigma equal to constant, which means throughout the disk the sigma is constant. Now so total charge q will be equal to integral sigma dA, and that's equal to sigma times integral dA, that's equal to sigma A, where A is the area of the disk. Let us discuss the area element dA in all the different coordinate systems. So dA in x, y, z coordinate system, you have dx dy, and dx dy will be in the direction of z, and dy dz in the direction of x, and dz dx in the direction of y. And this is for Cartesian coordinate system. Now for polar coordinates, we have r dr d theta, and this will be in the direction of r and theta in the direction of some n cap direction, both perpendicular to r and theta. Okay. Now this is for polar. Now for cylindrical, the coordinates are dr, rho, phi, and z. Now we can just remove this rho because we have already we'll be using it for volume charge density. So let us write down r, phi, and z. So r dr d phi in the direction of z. Then we have dr dz, dr and dz in the direction of phi, and r d phi and dz in the direction of r cap. So this is what we can do. Then one more coordinate system, that is spherical polar coordinates. For spherical polar coordinates, you have r theta phi. So the first one is r dr d theta in the direction of phi cap, then r sine theta dr d phi in the direction of theta cap, and r square sine theta, r square sine theta, uh, d theta d phi, d theta d phi in the direction of r cap. So depending on the surface, the area vector changes. So this is dA in the direction of phi, z cap, x cap and y cap. Okay, so this is it. So if it is spherical, sorry, Cartesian, you can use this area vector. If it is cylindrical, please use this one. Spherical polar coordinates, these vectors. So these are all different area vectors in the 3 directions. Now we have here 3-dimensional continuous charge distribution. Examples are cylinder, sphere, and you can also consider 3D box or a cube. Now the continuous charge distribution has the volume charge density given by volume charge density. So volume charge density is equal to given by rho, which is equal to dq by dv. Sometimes this is also written as dq by d tau, or dv or d tau as small change in the volume. This implies the charge dq is equal to rho d tau or rho dv. Now for uniform charge distribution, we have the total charge q equal to rho v, which we get from integral rho dv, and rho can be taken out because it is uniform, and integral of the dv gives you the total volume, that is rho times v. And if it is non-uniform charge distribution, your total charge q equal to integral rho dv, and this rho is not constant, as we have discussed. It varies according to the dimension of v. Now considering the volume element in all the 3 coordinate system, we do not have the volume element in polar coordinates. So volume element in Cartesian coordinate system, we have Cartesian is dx dy dz. There is no direction because volume element is a scalar quantity. Cartesian spherical, we have r square sine theta dr d theta d phi, and for cylindrical it is r dr d phi dz. So these are the volume element in different coordinate system. If your rho is in Cartesian, you should use dx dy dz. If rho is in spherical polar coordinates, we need to use r square sine theta dr d theta d phi. And we can also mention the limits of x, y and z, or x, y and z limits are from 0 to infinity for y and z as well. And for r theta phi, r it is from 0 to infinity, sorry, it is x is from minus infinity to plus infinity. Similarly for y and z. In case of spherical polar coordinates, r value is ranging from 0 to infinity, theta from 0 to pi, and phi from 0 to 2 pi. The cylindrical coordinates are from 0 to 0 to infinity, phi from 0 to 2 pi, and z from minus infinity to plus infinity. So these are the limits. And when you are considering the charge of the distribution, one has to consider the limits of the body in which the charge is present. For example, if you are considering a cube or a cuboid of length a, b and c, so a, b and c are the length, breadth and the height, then x value ranges from 0 to a, y from 0 to b, and z 0 to c, or whatever the length mentioned in the question. Here we are discussing vector calculus. Okay, so for the coordinate system that we know is the Cartesian coordinate system. Cartesian coordinate system, where the bases are x cap, y cap and z cap. That means any vector is a combination of x cap, y cap and z cap, and the conditions are x cap dot x cap equal to y cap dot y cap equal to z cap dot z cap equal to 1. Now similarly we can write x cap dot y cap equal to y cap dot z cap equal to z cap dot x cap equal to 0. This is just like the normalization for wave function, and this is similar to orthogonality condition of wave function. Now any vector A, as mentioned earlier, can be put in terms of x cap, y cap and z cap. So we can write A x into x cap, a y cap, a z cap. These are the ax, ay and az are x, y and z coordinates, and the range of x is from minus infinity to plus infinity. Similarly for y and z, both are all are from minus infinity to plus infinity. Now I am introducing an quantity called metric element. Metric element. So the metric element for the Cartesian coordinate system is 1 1 1. This each value corresponds to x, y and z coordinates, which means if I want to write some change dr, small length element, then dx into x cap, that means the matrix element 1 into dx into x cap plus another metric element 1 into dy y cap plus the third metric element corresponding to z into dz z cap. Now the each length element are dx, dy and dz. So this will be the corresponding length. The area element, this is the length element, so this what is we have given. The area element is given by, that means the small area ds vector is equal to first one dx dy. Dx dy will be in the direction of z cap, dy dz will be in the direction of x cap, and dz dx will be in the direction of y cap. So these are small area element in the Cartesian coordinate system, and this direction z cap, x cap and y cap will be always outward, and it's always as usual, obviously it will be normal. Now we have the volume element. Which is given by dx dy dz, which is equal to dv, or sometimes we may not denote it with d tau. Now for any vectors a, b and c, the volume is given by a dot b cross c. So kindly remember this. The next coordinate system is cylindrical coordinate system. For the cylindrical coordinate system, the bases are rho, phi and z, and as we have seen in the case of Cartesian coordinate system, rho cap dot rho cap equal to rho cap dot phi cap dot phi cap equal to z cap dot z cap equal to 1, and similarly rho cap dot phi cap equal to phi cap dot z cap equal to z cap dot rho cap equal to 0. Now any vector a in a cylindrical coordinate system can be represented by a rho cap plus a phi cap plus a z cap. So a rho, a phi and a z are the elements for the coefficient of rho, phi and z. And now we need to find out the limits of rho is from 0 to infinity. The range of rho is from 0 to infinity. The phi ranges from 0 to 2 pi, and z ranges from minus infinity to plus infinity. Okay, so the metric element we are denoting it by 1 rho 1, and it is denoted, the metric element is h1, h2, h3. And for the cylindrical coordinate system we say it is equal to 1 rho and 1, that is the metric element corresponding to rho is 1, metric element corresponding to phi is rho, and metric element corresponding to z is 1. That means any element, length element dr is written as d rho into rho cap plus that means here you need to write 1, that is the metric element 1, d rho into rho cap. Now you have the metric element rho d phi cap plus 1, that is 1 into dz z cap. So here there is we have added the metric element rho, since rho is the metric element corresponding to phi. Okay, so we can write it as d rho cap plus rho d phi cap plus dz z cap. Now if you want to convert it this cylindrical coordinate system to Cartesian coordinate system, we have to write this x as equal to rho cos phi and y is equal to rho sin phi, and the value of z is equal to z. The length element in the cylindrical coordinate system along each direction is given by d rho d phi and dz. So these are the length element. Now the area element is just take the product of 2, so it is d rho into rho d phi, so it is rho d phi. The second one is just multiply with d rho with dz, so it is, and you have to also write down the vector, that is z cap. Now I am multiplying this with this, so it becomes let us write down d rho into dz, which will be, if I write like this, d rho dz, it will be in the direction of phi cap, but since I have taken it in the reverse order, it should be always going in the cyclic order, 1, 2 and back. Okay, so if I have changed the order, I have to put a minus sign. Okay, now or what you have to write, rho d phi dz rho so let us write here rho d phi dz in the direction of rho cap, and one more thing you can write dz, also that is here we have already written this, you can change it in the form of dz d rho in the direction of phi cap if you go cyclic. Now the volume element dv, volume element dv is equal to, just take the product of all the length element, that is rho d phi dz, or you can also write it as d tau. So this is about cylindrical coordinate system. Third coordinate system that we are dealing with, that is spherical polar coordinates. Okay. So here we have the basis as r, theta and phi. Now as we have proceeded with the other two coordinate system, we will do r cap equal to theta cap dot theta cap equal to phi cap dot phi cap equal to 1, and r cap dot theta cap equal to theta cap dot phi cap equal to phi cap dot r cap equal to 0. So this is the normalizing conditions like we have in the quantum mechanics wave function, and this is the orthogonal condition. Now any vector in spherical polar coordinates like A can be written as AR into r cap plus A theta into theta cap plus A phi into phi cap, where AR, A theta and A phi are the elements in the spherical polar coordinates corresponding to r cap, theta cap and phi cap respectively. Now coming to the range of r varies from 0 to infinity. Please kindly note it is not from minus infinity to plus infinity, it is from 0 to infinity, and theta is moving from 0 to pi. Again please note it is from 0 to pi and not the entire 360, it is 0 to pi, and the phi varying from 0 to 2 pi. Okay. Now let us also write down the metric element in spherical polar coordinates, that are 1 r and r sine theta. So this is the metric element. So any vector dr can be written as that means dr is equal to any length element. Okay. So dr, that means the metric element corresponding to r, that is 1 into that dr, small change in dr, into r cap, the unit vector, plus the metric element corresponding to the theta, this is r, this is for r, this is for theta and this is for phi. So metric element corresponding to theta is r, and it is d theta, r d theta, in the direction of theta, that is theta cap, plus you have to write down the metric element corresponding to phi, which is r sin theta into d phi into phi cap. So this is the entire vector, or the length, small change in length is given by dr r cap plus r d theta theta cap plus r sin theta d phi phi cap. So this is corresponding to the length on radius. This is theta, r d theta, and r sin theta d phi, that is corresponding to angle phi. Now the length element we have, once again you can write that length elements. What are the length element corresponding to each of the coordinates, that is dr and r d theta and r sin theta d phi. Now we have the area element. So area element is nothing but 1 2 into the direction of third. So dr into r d theta. So let me write r d theta, just the multiplication, and in the direction of the third, that means in the direction of phi, because area element is a vector. Okay, this is one. Now the next one is 2 into 3 in the direction of the other. So r d theta, so you can write r d theta times r sin theta d phi. So r square sin theta into d theta d phi, and it should be in the direction of the r. Okay, so plus, now you have to do this 1 2 in the direction of 3. So r dr sin theta, r dr is there. Okay, so r sin theta dr d phi, and it should be in the direction of theta. So this is theta cap. So this is phi cap direction unit area vector. This is in the direction of r cap, and this is in the direction of theta cap. Now coming to the volume element. Product of all the three, that is r. So r square dr sin theta d theta d phi. So okay, fine. So r square sin theta d theta, okay, it's dr d theta d phi. Okay, so or you can write it as r square dr sin theta d theta d phi. This is because when you integrate, you can, this is the first term, this is the second, and this is third. Okay, this is volume element dv or d tau. Okay, yeah. So let us also write down what are, according to the coordinates x, Cartesian coordinate, with how you can write the x in terms of spherical polar coordinates. Okay, it is r sin theta cos phi, y is equal to r sin theta sin phi, r r sine theta sine phi, and z equal to r cos theta. Okay, so kindly remember the points noted. Here we have a question. The question is the linear charge density for a rod is given by lambda is equal to ax plus bx squared for the length of the rod L. Find A by B if total charge on the rod is 0. Now we have the question and the total charge is given as 0. So total charge on the rod is lambda dx, integral lambda dx, and the rod has a length ranging from 0 to L. Now that is given by integral 0 to L. Lambda is ax plus bx square dx. Now that gives us ax square by 2 plus bx cube by 3 and the limits 0 to L. Now this gives us al square by 2 plus bl cube by 3. Now that gives the idea that the total charge is equal to 0. Now it says that al square by 2 is equal to minus bl cube by 3. Now send the others to the other side. A by b is equal to 2bl cube with a minus sign, sorry, b has to be 2l cube divided by 3l square. So a by b is equal to minus 2 by 3 times L. So if a by b equal to minus 2 by 3 times L, the total charge on this rod will be equal to 0. So this is our another question. For a circular ring of radius 1 unit, the linear charge density lambda is given by lambda naught sine theta in the range 0 less than theta and less than pi, lambda naught cos theta in the range pi less than theta less than 2 pi. Now this is the lambda given, and we are asked to find lambda naught if the total charge on the ring is E. Now so the total charge on the ring Q is equal to integral lambda and this and dx, you can write it as r d theta, where r is the radius of the circular ring. So r d theta. Now we know that r has a unit, it is unity, and so we can write integral lambda d theta, and the theta where is lambda given? Lambda is given as lambda naught sine theta, and in the range 0 less than. So you can write that you can split the interval. So 0 to pi, lambda equal to lambda naught sine theta, lambda naught sine theta d theta plus integral pi to 2 pi lambda naught cos theta d theta. Okay. Now this comes to be equal to lambda naught sine theta is integral is minus cos theta, so minus cos theta and value ranging from 0 to pi, plus here you have lambda naught sine theta, here the value is ranging from pi to 2 pi. So here you have lambda naught, and since it is minus, you can go with the lower limit first. Cos 0 is 1, cos pi is minus 1, so minus 1 plus lambda naught sine theta, value from 0 to pi to 2 pi gives you 0, so second term vanishes, so it is 2 times lambda naught. So 2 times lambda naught is equal to E, so which means lambda naught equal to E by 2. So your option is option D. For a circular disc, sigma is given by sigma naught r cos square theta. So this is the value of sigma. We are asked to find total charge on the disk. So total charge on the disk. Okay, now the formula is Q is equal to total charge equal to sigma dA. Now we need to find what is dA. dA is, so since it is circular disk, we can consider it as polar coordinates. So for polar coordinates, the disk has an area equal to r dr d theta, okay, so Q is equal to integral sigma is sigma naught r cos square theta into r dr d theta. Now we need to know the limits of r and theta. R is ranging from 0 to capital R. Let us consider capital R as the radius of the disk, and theta value is ranging from 0 to 2 pi. Now the total charge Q is equal to integral sigma naught r and r, it is r squared dr, and this is cos square theta d theta. So now just splitting the integrals. Integral sigma naught is a constant which can be taken out, r square dr integral cos square theta d theta. So r square is ranging from 0 to capital R, cos or d theta, theta value ranging from 0 to 2 pi. So that gives us sigma naught r cube by 3 from 0 to capital R. Cos square theta, you can use cos square theta equal to 1 minus sine square theta by 1 minus sine square theta by 2. That is 1 plus cos 2 theta, 1 plus cos 2 theta by 2, and this integral cos 2 theta integral from 0 to 2 pi gives us 0, so 1 by 2, so 1 by 2 from 2 pi minus 0, so 2 pi minus 0, so this gives us sigma naught r cube by 3 times half of 2 pi is pi, so this gives us sigma naught pi r cube by 3. Two problems based on 3 dimension. We have rho is equal to dq by dv or d tau. Then dv, what is dv? dv in first let us consider cylinder. dv is r dr d theta dz, r dr, sorry, it is d phi dz. R is ranging from 0 to capital R, phi varying from 0 to 2 pi, and dz varying from it is from minus z, minus infinity to plus infinity, but this one can be considered as a finite cylindrical box, so you can range from 0 to capital L, where L is the height of the cylinder. So dq dq is equal to rho dv, integral dq is equal to q equal to integral dq, that is equal to integral rho dv. The question number 1, the question is rho is given by rho naught r for r less than or equal to capital R. That means until small r equal to capital R, the value of rho is rho naught r, and after r it is 0. That means for r greater than capital R, the charge density is 0. So it is like this. You have a cylinder, so this is from 0 to capital R. That means charge density is found only in this region. After this region there is no charge density because this is air, or it is independent of charge density. So we have to mention that the rho exists only up to capital R, and above this 0 to L also there is no charge. Beyond this length, let us say this is 0 and this is L, beyond this length there is no charge. So let us find out the total charge Q, which is equal to integral rho dV, that's equal to rho naught R, that is rho naught R varying from 0 to capital R. Sorry, we will write down the other quantities. Rho naught R into r dr d phi dz, r dr d phi dz, splitting it, integral rho naught, this is r, so r square dr, so this is from 0 to capital R, and d phi integral is from 0 to 2 pi and dz integral from 0 to L. So this gives us rho naught r cube by 3. So rho naught r cube by 3 from 0 to capital R d phi 0 to 2 pi into dz length. So this gives us from r cube, so rho naught capital R cube by 3 into 2 pi L. So this is the total charge present in the cylinder. Coming to the spherical charge distribution, so sphere, as we have discussed, dV is equal to r square dr sine theta d theta d phi. R is from 0 to capital R, theta ranging from 0 to pi, and d phi varying from 0 to 2 pi. Now total charge Q is equal to integral rho dV. Now as a question we can do this problem. Rho is equal to some k by small r for r less than or equal to capital R, and outside R there is no charge. That means you have a sphere, and up to capital R you have this as the charge density, and after the radius there is no charge density because there is no sphere present or to accumulate charge. So Q is equal to integral rho dV, that's equal to rho is equal to k by r, dV is r square dr integral sine theta d theta integral d phi. R is ranging from 0 to capital R, theta from 0 to pi, and d phi from 0 to 2 pi. So this gives us k by r, and r get cancelled, so it's kr from 0 to capital R sine theta d theta. Sine theta is integral is minus cos theta varying from 0 to pi, and d phi value 2 pi. So this gives us kr cos theta, first you give to 0, 1 minus 1, that is 2, 1 minus 1 times 2 pi. Oh wait, we have made a mistake. So it's r and r, so it's r square by 2, so it's kr square divided by 2. Alright, now so kr square by 2 into 2 plus 4 pi, so 2 get cancelled, so it is 2 pi kr capital R squared. So this is the total charge present in this sphere. As practice work, you can try solving this problem. Question number 1 is lambda is equal to a divided by x square plus a square. So this is linear charge distribution. It is a rod of length 0 to L. Now Second one, sigma is equal to sigma naught by r sine square theta. This is disk of radius capital R. Third one, we have the 3 dimension for cylinder. Cylinder rho is equal to k by r sine square phi. Oh, this is cylinder of radius r, length L. Now fourth one, it is sphere. Rho is equal to 2 divided by r sine theta, and this has a radius r, and fifth one is also sphere, where rho equal to c divided by r into r square plus c square for 0 less than r less than capital R. Sixth one is also sphere. Rho is given by k divided by r for r less than 0 less than r less than capital R by 2, and this is k naught by r. This is k naught r for r by 2 less than r less than capital R. So these are the problems for workout. Kindly do the problems.